Question 1 is a question on statics. You are given a solid ball with a diameter of 32 cm that is supported against a vertical and frictionless wall using a thin 30 cm wire of a negligible mass. Now the first part asks you to draw a free body diagram for the ball and use it to find the tension in the wire. So the free body diagram looks like this. You have a tension acting on the ball and a certain angle to the horizontal. You have the weight of the ball acting downwards, and then there's also a normal force acting on the ball due to the wall. Now, to find the angle theta that the string makes with the horizontal, you have to use Pythagoras theorem. In this case, we know that the hypotenuse is the length of the string plus the radius of the ball, which is 0.3 plus 0.16, giving 0.46 meters. And the adjacent side is simply the radius, which is 0.16 meters. Using the ratio cosine theta, you can easily solve for theta equal to 70 degrees. And then from here, to find the tension in the string, we sum up forces in the y direction because it is statics. So the right hand side is 0. And we know that in this case, t sine theta minus the weight mg is equal to 0. From here, we easily solve for our tension. To find the normal force, we sum up forces in the x direction. Again, is equal to 0 because it's a statics problem. So t cosine theta minus n is 0. From here, we solve for n, giving us 163 newtons. In this question 2, you have two blocks of mass, one lying on a ram and the other hanging vertically from a certain pulley. They are connected by a light inextensible string over the pulley. So you are given that mass 1 is 20 kilograms. The angle that the ram makes with the horizontal is alpha equal to 53.1 degrees. The coefficient of kinetic friction is given as 0.4. So the question asks, what must be the mass m2 of the hanging block if it is to descend 12 meters in the first 3 seconds after the system is released from rest? The second sentence here actually is a question on kinematics. From the displacement 12 meters and the delta t change in time 3 seconds, we are able to determine the acceleration of the system. The first step is to find the acceleration. Let's first draw the free body diagram for the mass 2. You have a weight m2g pointing down. You have a tension pointing up. We set the positive y direction to be pointing down. We are given that y0, the initial y position is 0 meters. Yt is 12 meters. T is 3 seconds. The initial y velocity v0y is 0. Using this kinematic equation, we are able to easily solve for our acceleration, giving us 2.667 meters per second squared. After we have found the acceleration, we make use of Newton's second law, summation of forces in the y direction equal to ma(y). So m2g minus t is equal to m2a. However, we have two unknowns, m2 and t. So in this case, we simply express our tension T in terms of m2, giving us equation 1. Now to solve for our mass m2, we need another equation, and that comes from your mass m1. So let's now draw the free body diagram for mass m1. We have a weight m1g acting down, the frictional force acting opposite to the direction of motion, Fk equal to mu kn. Our tension T is pointing up the ram, and of course we have a normal force acting perpendicular to the ram. We set our coordinate system to be x pointing up the ram and y pointing away from the ram, upwards. So that's our free body diagram. We are given that m1 is 20 kilograms. So our first step is to use the first law in the y direction. Summation of forces in the y direction is equal to 0. From there, we obtain an expression for n, the normal force. Next, we use Newton's second law in the x direction. Sigma fx is equal to m1a. So the forces in the x direction are the tension positive minus mu kn minus m1g sine alpha. That is the component of the weight in the x direction. the right hand side is just m1a. Now, this a here is the same as the a calculated previously, because the positive x direction for mesh 1 is in the same direction as the positive y direction for mesh m2. So they are equal. So now we proceed to solve for our tension T, and we obtain 257.15 newtons. From equation 1, we have T equal to m2 bracket g minus a. So the m2 is equal to T over g minus a. We use our previously solved value for T, substitute inside and obtain our final answer, m2 equal to 36.1 kilograms. Question 3. Block B with mass 5 kilograms rests on block A with a mass of 8 kilograms, which is in turn on a horizontal tabletop. There is no friction between block A and the tabletop, but the coefficient of static friction between A and B is 0.75. A light string attached to block A passes over a frictionless, massless pulley, and block C is suspended from the other end of the string. What is the largest mass that block C can have so that blocks A and B slide together when the system is released from rest? In this question, you can imagine that if the mass of C is so large, then the acceleration of the system will be very high. In this case, this means that the acceleration of B is also very high if B were to move together with A without slipping. And if you look at block B, the only force that can act on it is the static frictional force applied on B by block A. So we all learned that the static frictional force can only reach a maximum value if the acceleration is so large. The force needed to sustain this large acceleration will exceed the maximum static frictional force, and block B will then slide with respect to block A. But we do not want this to happen. We want block B and A to move as one body. Therefore, block C can only have a certain maximum mass, and that is what the question is asking. So, if blocks A and B are to move together as one unit, when mass C takes on its largest value, then the force acting on block B is the maximum static frictional force given by mu Sn. In this case, we consider the 3 blocks and one single system, so the total mass is just 13 plus mc kilograms. So, since we consider the 3 blocks as one single system, our free body diagram is very simple. We have only one force, mcg, acting downwards. There is no friction between the table and block A, so there's no force on the AB combination. And the normal force on block A doesn't come into the picture because it is normal to the direction of motion, which is given by the S direction. So at the end of the day, there's only one force acting on the system, and that is the weight of block C, mcg. So we apply Newton's second law in the S direction. Summation of forces in the S direction is equal to m total times acceleration as. So mcg is equal to 13 plus mc times as. Now we have 2 unknowns here. One is the mass of block C, the other one is the acceleration of the whole system. We have 2 unknowns. So we need one more equation to solve for our mass of C. And that will come from the free body diagram of block B. So if we draw the free body diagram of block B, we have 3 forces acting on it. First, the weight mbg acting downwards, the normal force acting upwards, and also the maximum static frictional force acting to the right. So we apply Newton's second law in the S direction. Summation of forces in the S direction is equal to mb times as, so that mu Sn is equal to mb as. From here, we can easily solve for our acceleration in the S direction. So as is given as 7.35 meters per second square. Now, using this value of as, we can easily go back to equation 1 and solve for our mass of block C. So after some algebraic manipulation, you arrive at MC is equal to 39 kilograms. Question 4. You're riding inside an elevator on the way to the 18th floor of your dormitory in SIT. The elevator is accelerating upward with acceleration A equal to 1.9 meters per second squared. Beside you is a box containing your new computer. The total weight is 28 kilograms. While the elevator is accelerating upwards, you push horizontally on the box to slide it at a constant speed towards the elevator door. If the coefficient of kinetic friction between the box and the elevator floor is mu k equal to 0.32, what magnitude of force must you apply? So in this question, there are two important directions, the y direction upwards and the x directions horizontally. You are given the fact that there is an acceleration A in the y direction, whereas in the x direction, there is a kinetic frictional force, and the box is moving at a constant speed. So let's see how we solve this question. As a first step, we always draw the free body diagram. Now in the x direction, which is to the right, we have the force that you are applying to the box as you push it to the door, called F. Now opposite to this force is the kinetic frictional force mu k n. In the y direction, we have the normal force n pointing up, and we have the weight mg pointing down. We are given the fact that there is an acceleration ay equal to 1.9 meters per second squared pointing up in the positive direction. So we first apply Newton's second law in the y direction. Summation of forces in the y direction is equal to may. N minus mg is equal to may. From here, we can easily solve for our normal force n. The next step is simply to apply our Newton's first law in the x direction, since it is moving at a constant speed in the x direction. So summation of forces in the x direction is equal to 0. That gives us F minus mu kn equal to 0. From here, we can easily solve for F. Last question. You're riding in a school bus as the bus rounds a flat curve at constant speed. A lunchbox with mass 0.5 kilos, suspended from the ceiling of the bus by a string 1.8 meters long, is found to hang at rest relative to the bus when the string makes an angle of 30 degrees with the vertical. In this position, the lunchbox is 50 meters from the center of curvature of the curve. What is the speed of the bus? So this question has to do with uniform circular motion. As always, the first step is to first draw the free body diagram of the hanging lunch box. We have the tension force acting at an angle of theta to the vertical, and we have the weight of the box 0.5 g pointing down. We set our positive y direction pointing up and our positive x direction pointing to the right. The radial acceleration is pointing to the right, is given by A radial equal to v squared over r. We are given r, which is the radius of the curve. We are also given that the length of the string is 1.8 meters and that the angle theta that it makes with the vertical is 30 degrees. So first step, summation of forces in the y direction is equal to 0 because in the y direction there's no acceleration. So we have t cos theta equal to 0.5 g. So from here we can easily solve our tension T. In the second step, we apply Newton's second law in the x direction because there is a radial acceleration pointing to the right. So in this case, t sine theta is equal to ma radial, where a radial is simply our v squared over r. From here, we can easily solve for our v, giving us 16.8 meters per second.